Welcome back to today's lecture, and this one which we are going to do is basically on using different kinds of optimizers. So, as you have learnt on your update rules over there, so one of the ways of doing it was using something called as a gradient descent, or which is like for within every single epoch you find out what is your error, then find out a gradient of the error, and then use that gradient of the error multiplied by something called as learning rate, and that error over there is what is used as an update over the weights itself. So, that was the most simple part over there. Now, along with that, while there are advantages, disadvantages, it's pretty simple to derive it out, and was one of the first ways of doing any sort of an learning rule which was defined. Now, these whole problems as such are also within gambit of engineering solution which is called as optimization. Now, the reason why this is called as optimization is from the fact that you know that you are never able to go down to a zero error. Technically, you will, most of the cases you will never be reaching down a zero error, but you will be coming down to a very low error on the error surface over there. Now, the whole purpose of optimization is like to find out an say agreeable solution of that minimum error point where it's good for you to go down. Okay. Now, as it turns out, so gradient descent is not the only way of coming down over there. There are in fact multiple different ways of that. So, one of them is called as stochastic gradient descent operator. The other one is an learning rule using something called as an adaptive momentum or ADAM optimization technique. So, today I am just going to, while in the earlier lecture we have covered down on the theoretical aspects. So, this is about how do you actually create your whole network to use any of these optimizers, and we will come down to using something generically within an optimizer package. Okay. And instead of trying to write down your vanilla gradient descent as an update rule every single time within an epoch, here is where you will be using something called as an optimizer dot step, as we have used in some earlier examples as well. So, here is just to show you what is the effect which happens down with two different optimizers. Okay. Now, we will stick down to just using stochastic gradient descent and adaptive momentum or ADAM optimizers. So, as in for whatever we have been doing with the earlier classes as well, the initial header is just a loader of all the important functions which are needed over there. We start with doing our data loader. So, the data which we are using is mnist with a batch size of 100. So, every single batch it is going to do 100 samples loaded from the hard drive and then use it for the whole purpose over there. Now, we would stick down to the best possible approach which we found out in the earlier case on different kind of update system. So, one was where you had done one update at the end of an epoch, the other one was there was an update every batch, and the remaining was where there was an update for every single sample which goes into the network and every epoch. Now, while you did find out that in the first case it was taking the least amount of time when you were updating it once within an epoch, in the second case it was taking almost the same amount of time, but you are updating it multiple times within an epoch, and as a result of this multiple times of revision within an epoch, it was going to a much higher performance. So, your error was steadily much below than what you had in the earlier case, and your accuracies was also high. So, we are going to stick down to this best possible approach which takes the least amount of time, comes down to the best accuracy at the fastest rate, and that is batch update. So, we just stick down to that, have our batch training over here ready, and then just check out if our GPU is available, and that is there, and so we define our network. So, the network is plain simple neural network for this classification problems. It takes in a mnist of the size of 28 cross 28 or 784 neurons which are connected down to 400 neurons in the first hidden layer. That is connected down to 256 neurons in the second hidden layer. The intermediate transfer functions for each of them is a rectified linear unit or a ReLU block, which means that any activation which is negative is clamped onto 0 level. Any activation which comes out of this is if the input to this ReLU layer is positive, then it just preserves over there. So, it creates a positive only side of an output in a linear way, and negatives are all 0. So, that was ReLU. And then on the next part of the layer, which is my, so while the previous part is what we have been defining as the feature discovery layer, the next part of the layer is what we define as the classification part of the layer, and this is where you take down from 256 neurons in your hidden layer and connect down to 10 neurons on your output side, and they correspond to the 10 classes in which your classification is going down. And finally, there is this forward pass of the definition, or how what happens when you have the data given down. So, first it does a forward pass over the layer 1, which is the representation learning layer. The second time it does a forward pass over the layer 2, which is my classification mapping layer. Okay. Now, what I choose to do over here is basically introduce 3 different kinds of networks. Now, one you have done this in the earlier case when we were doing down multiple kinds of cost functions in its way, but then the question over here would, we are just using 2 optimizers, then why do 3? Now, when you go down with stochastic gradient descent, you actually have 2 different kinds of SGDs which we will be dealing with, and for that we just try to introduce it in 2 different variants, and that is where 3 different networks are defined over here. Okay. Now, going down with the same kind of an argument as we had in the earlier case when we were trying to use different kind of cost functions. Okay. So, over there the whole point was that this criterion was changing at every time. So, if it was a regression problem, then you had 2 different regression criterion points, either as an MSE loss or L1 norm loss. If it was a classification, then we had done it with the cross entropy loss, with the negative log likelihood loss, and with the multi-margin loss criteria. So, here we are just going to stick down to one of the classification losses, which for us is going to be cross entropy, just one of them. The only thing which we are going to vary over here is this optimization technique over there. While in the earlier cases we are just sticking down to plain vanilla gradient descent, over here we are going to have down 2 variants of SGD and one of the variants of Adam taken down. Okay. So, now if you go over here, so you see that I have 2 different I have the 3 different optimizers which are created. So, the first one is from my optim package, I call down my function called as SGD. Okay. Now, this SGD, what it takes in is just a learning rate of 10 power of minus 4. The second one is where I have an SGD call down along with a momentum of 0.9. Okay. So, where this actually significantly changes is that every single epoch, after every single epoch that SGD has operated out, it will add a significant amount of momentum to the gradient itself. So, while in the earlier case with vanilla gradient descent you had your learning rate which was eta. Okay. So, this eta is what gets multiplied onto that, but along with that we are just going to add down an extra momentum factor to the complete aspect over there. So, this is the whole eta times of nabla j plus a certain DC factor which is added down, and it has been found that with adding this momentum, typically what happens is if you are very close down to one of these saddle points, so maybe your global minima is over here, but you are actually over here. Now, this being a local minima over there, your error is still going to settle down to 0 and you will not be able to come out, whereas if we have a DC error added down over there, so it knows that it is going to somehow climb up over there over a few epochs and then settle down to this exact point of my global minima over here. So, that is the point which goes down with adding down a momentum to my stochastic gradient descent. The third one which we do is an adaptive momentum approach. The difference which comes down from a stochastic gradient descent to an adaptive momentum approach is that this momentum value which is given down as a constant, it actually adapts itself over epoch, looking at how many number of times I have the total number of epochs which has run down, as well as the change in relative change in errors which have been occurring down while it is going down the number of epochs, and as it keeps on going lower and lower, this momentum factor also keeps on adapting itself and coming down. So, this is what we had learnt in the theory, and today we are just going to put that into practice. Okay. So, for each of these 3 different networks which apparently get trained by 3 different optimizers, I just have 3 different variables to put down my accumulate my accuracy as well as my loss, because this is just a classification function. So, I am just taking in accuracies and not similarity measures in terms of MSE or anything, but you can actually take all of these examples and plug it into your regression loss function based examples as well. So, if you are just training an autoencoder for representation learning, or say for denoising, you can use the same kind of a concept. So, say a denoising autoencoder, a denoising sparse autoencoder can also be trained using either an SGD or an Adam or whatever you choose to like over there. So, we have trained it with an Adam though, so because it was coming down to a much faster one, but by now you have understood about what is the difference which comes down with batch updates versus single updates versus one epoch based update. So, you can go back with the same kind of a learning option over there. Now, today we will be looking into the difference what comes down between an SGD and an Adam, and while all the earlier experiments have been with the standard vanilla gradient descent, you can actually bring it up to that level and compare it out completely. So now within my epoch, what I am going to do is, since there are 3 networks and I need to compute out number of corrects and number of the loss over there. So I just initialize these variables within every single epoch over there. Now within over there, what I do is, within an epoch, it's going to load down in batches. So my batches over here of a batch size of 100, because that's what we figured out as the optimal way of training down a network. And then it starts its own function over there. Now the train function within every epoch, what it does is, the input argument to it is a network. Then you have the optimizer, whichever you are going to use. So as in optimizer 1, 2, 3 is what gets defined over here earlier, and then you can keep on doing. So let me run this part of it, which is the general function for training with the so the training function as a call, and then we can start with our training within an epoch. Okay. So now I have my 3 losses coming down from my 3 different optimization functions for the same network, though it's just different pointers, so that you can track out which one is getting updated at what loss, and then you find out your total loss over that whole all the samples within one single batch, and then accumulate it out over all the number of batches in your epoch, and then you have the loss per epoch coming down to you. The next part is basically to find out what is the accuracy over there, and for that we will be making use of the test data set and then making it dominant use via the test loader for this data set itself. And then for every single network, we are just going to do a feed forward over the data which is present in my input, and then get down what is my predicted value, and then find out how many number of it are correct for, say, the network 1, then the total number of corrects for network 2 by doing the same thing, except for that the network over here changes. And during testing, it is just a feed forward inferencing engine, it does not have to do anything with optimizers during testing itself, but this testing is there within every epoch. So once it is updated within an epoch, I just want to see what is the performance going down over there, and finally we just end up plotting this one. So these parts of the code are what is what are more familiar with in the earlier examples, and it is just a direct takeaway from them. The only reason we put it down is so that you have one distinct place where everything is written from scratch for every single thing which you are doing, and you can make reuse over how you choose to do it, and these can act as standard templates. So now let us look over here. You see that typically an epoch does not take quite long to go, although we did not put the timer over here, but sometimes you can actually put the timing engine over there. Now when I am trying to do it with just SGD over here, you see that I have somewhat of an accuracy of 11%. With SGD with the momentum, I did go down to an accuracy which is higher over there, and one of the reasons is that say it was hitting down this local minima point within every single within any of the batches within an epoch. So it was able to actually dislodge itself and go down towards other global minima points, or it's still continuing to do in that way. Whereas on the other case, you see with Adam coming down, the loss has decreased significantly, and the accuracy itself at the end of first epoch. So at the end of first epoch, you just had 400 times of an update onto it, which is the total number of batches, sorry, 600 times of an update. You have batch size of 100 and your total number of samples are 60,000. So 600 times is what is updating within every single epoch. Now over there, it already is at a point of 91%. Now that is large, seriously large number, which you have seen in the earlier cases. And one of the reasons is the advantage of getting this adaptive momentum coming into it here as compared to the other ones. Now this does bring you to a point that whenever you are trying to use an Adam over there, one is that your losses are definitely much lower, although it's the same loss function. I'm not changing that different loss functions, that they will have different dynamic ranges. It is the same loss function across which it's pitted down and it's being compared. Now on the final performance on accuracy, you would see that with the stochastic gradient descent, it finds really hard to actually pick up. It will take a long time in order to go down over there. Whereas with the with some sort of a momentum added over there, it comes down closer to actually going down to the final accuracy. Whereas with Adam, it really comes down to a sweet spot on the final convergence accuracies over there, and that's an advantage which you get down with this adaptive momentum. Now the method is not very old; it's actually a new. It's this say this decades itself one of the major contributions. If you look on the other side of it, going down by plain vanilla gradient descent to a stochastic gradient descent. So, these were things which are 30 to 40 years older, and in the last 10 years we have a method which is much more superior to that, and something which is finding its own popularity and gaining its significance for all the different kind of applications which we are going down with. So, in the earlier cases you have seen that we have been using Adam for certain number of cases in order to just within 10 epochs come down to a good convergence and show you this convergence curves. The reason is that if we flow down with this, say stochastic gradient descent or vanilla gradient descent, instead of just 10 epochs, it is going to take me really long. I mean, I would possibly have to continue for 1000 epochs or something. So, this curve to reach down somewhere over here, which is closer to it. Now, in order to just come down to a tractable time, an adaptive momentum approach or an ADAM is something which is more appreciable, and on this note I would definitely go down and suggest that for a lot of problems ADAM works out. However, you need to keep one thing in mind, that your batch sizes need to be significantly large. So, we are handing down batch sizes of about 100. The moment you come down to smaller batch sizes, say batch sizes of 10 or 12 or 16, ADAM might not significantly prove as a good option, and in those cases rather than trying to go with ADAM, it is easier that you actually stick down to plain vanilla gradient descent or a stochastic gradient descent approach. Now, this is up to you. We have small patches of 28 cross 28. The moment you go down to large sized image, say 224 cross 224, and in the next lectures we will be starting with convolutional neural networks, and that is where you will be dealing with significantly large sized images, not those stamp sized and thumbnail sized images in any way, and that is where you will be seeing where the difference comes in. Now, going with those large size images, the amount of viable RAM which is available to you to run any of your codes becomes lesser and lesser over time, and your batch sizes need to be appropriately decreased. So, that is where you would now start facing a problem, that can I use ADAM at all? If I cannot use ADAM, then will my vanilla gradient descent or my stochastic gradient descent come down to that kind of a convergence at a much better way. So, this, as we keep on going down with those examples of large sized images, you will be having a complete feel about how it works out. In fact, we will be going down on with multi-class classification problems as well, and then also trying to do down temporal classifications over videos, and that is where you find these of great use. So, with that we come to an end of understanding things with our autoencoders and using those autoencoders and just simple neural networks to understand what happens down with different cost functions, different kind of learning rules, different kind of optimizations, and then how they can be used intermittently exchangeably between each other with a lot of scratch pads. Next class, next week onwards, which is where we start down with our CNNs or convolutional neural networks, and then on I am not going to get back any more onto these kind of rules and updates and techniques, because they just remain same whether you are using a fully connected versus whether you are using convolutional operator over there. The only thing which is going to change over there is the architecture is much more elegant, it is much more expressive, and the compute around that architecture is also something which is intriguing. So, we will be getting into more details of those as we keep on discussing. So, till then stay tuned and keep on enjoying for the next subsequent weeks.